going to define an Eisenstein series, which is a type of automorphic form. So recall that an automorphic form satisfies three properties. One is that it is invariant under the action of gamma naught n. So here I'm talking about weight 0 automorphic forms with trivial character. And level n. The second condition is that it is an eigenfunction of the Laplacian. And the third condition is that it grows sub-exponentially. At every cusp. And we observed that y to the s and y to the 1 minus s were eigenfunctions of the Laplacian. Which, recall, was defined to be this operator. So one way we can use this to build an automorphic form is to just take this function and average it over the group gamma naught n. And here I'm going to put a question mark because this is not going to be quite right. But the idea would be to sum over all the gammas in gamma naught n, and for each of them, look at the imaginary part of gamma z to the s. And okay, this is essentially automatically gamma invariant, right? Because gamma naught n is a group, so if you were to multiply by some fixed element, right, this is the same as gamma in gamma naught n of the imaginary part of, say, g gamma z to the s for any g in gamma naught n, because again we're just we're summing over the group, so you can just you're summing over all the elements of the group one way or the other, essentially. So this is automatically gamma invariant, and it is also automatically, essentially, an eigenfunction of the Laplacian, right? Because right here, every time we have a y, this is the imaginary part of z. So this imaginary part of gamma z, I mean, this is y. This is basically y to the s after you've applied this transformation. And the same way that y to the s is an eigenfunction of the Laplacian, because this is gamma invariant, this whole thing is going to be an eigenfunction of the Laplacian. So we've satisfied 1 and 2, so that looks pretty promising. But the problem here is that we fail this growth condition, and we fail it quite spectacularly, because it turns out that this quantity that we've written down is actually just infinity, right? This diverges for every z. So that's bad news. This doesn't even make sense, it turns out. And the reason why this is because there's this matrix 1, 1, 0, 1 in gamma naught n, and this has the property that 1, 1, 0, 1 acting on the point x plus iy gives you x plus 1 plus iy. So it just shifts the the x coordinate over 1. It shifts the real part over by 1. And it doesn't change the imaginary part. So if we're summing over, say, just this subgroup, so let me define gamma infinity to be the subgroup generated by the matrix 1, 1, 0, 1. So more explicitly, this is the subgroup 1, m, 0, 1 for all integers m, and it's a subgroup of gamma naught n. So even just summing over the subgroup, we get an infinite sum, because there are infinitely many elements in the sum, and you just get whatever y to the s was for that element for all of them. So this is the problem. So the thing to do then is instead to look at the sum not over all of gamma naught n, but the sum over the quotient of gamma naught n mod gamma infinity of the imaginary part of gamma z to the s. And this makes sense because here we just pointed out that when you act by this this matrix, you don't change the imaginary part of your number. So when we quotient by gamma infinity, we're not changing the value of y, so we don't have to worry about, say, which representative in this coset we take when considering this series. They all have the same imaginary part. So this is going to be our what's called an Eisenstein series. I'm going to write EZS. And this is an automorphic form this is a weight 0 automorphic form of level n in trivial character. And there are some variants that are also going to be useful. So one important variant is what about if we want a character, right? So recall that we're going to define chi of A, B, C, D to be chi of D, or here chi is a Dirichlet character. And there are going to have to be some restrictions on chi. Here, chi, it has to be a character mod n, and the reason why it has to be character mod n is because we're working on gamma naught n, and this isn't multiplicative if chi is not a character mod n. And you can check by just looking at the product A1, B1, C1, D1 times A2, B2, C2, D2, and you can compute what the lower right entry is and see that it's not multiplicative unless chi is a character mod n. And the second thing that we're going to need is that chi has to be even. And so why does chi have to be even? Well, remember that we're taking gamma naught n to be some subgroup of SL2Z and not PSL2Z, which, recall, was SL2Z quotiented by plus minus the identity. And what that means is that we have minus I in our group up here. And if we look at the sum, so the sum that we're going to end up getting is E ZS chi is going to be equal to some gamma in gamma naught n mod gamma infinity. And then here we're going to have a chi of gamma bar, I'll explain that in a second, times the imaginary part of gamma z to the s. And if chi were an odd character, then for every gamma you would also have a minus gamma in here, and so the sum would just be identically 0 as written. So sum will be identically 0. So there are ways to make sense of other characters, characters that aren't mod n or characters that are odd, but for this course I'm always gonna require these two things of chi. And the reason why you have a chi bar here is because remember that you want E gamma z s chi. If you want this to be automorphic weight 0, level n, and character chi meaning this has to be chi gamma. Let me use a different letter than gamma here. If we want this to be chi g times E ZS chi, well, we can just use the definition that we wrote out here. This is going to be the sum gamma in gamma infinity quotient in gamma naught n, and here we're going to have a chi bar of gamma imaginary part of gamma gz to the s. And now what we can do is we can make the change of variable. Instead of writing gamma, let's write gamma g inverse. And then our sum is still the same. We're still summing over the entire group. And what we see is that here we're going to get chi of gamma g inverse bar. And then here we have the imaginary part of just gamma z to the s, because we've had a GG bar. Maybe I'll write that out explicitly. Oops. And then, of course, here, this chi of G inverse, or chi bar of G inverse, this is, we can factor this out, sum of the usual thing, and then this is going to be equal to chi G times the sum of what we had before. So here this dot 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 is this thing. So that's why we put a chi bar here, so that it's automorphic in the way that we want. And finally, I should say that this definition that E ZS chi equals this series, well, let me just reference the series above actually. So this definition that we wrote down here, this is for the real part of S strictly greater than 1. And the same also for this definition. The real part of S has to be strictly greater than 1. And why is this? Well, recall that the imaginary part of gamma z is the imaginary part of z over absolute value squared of cz plus d. And this is some elementary calculation. We're here, gamma is ABCD. And so what that means is that this sum is equal to a sum over the imaginary part of z to the s over cz plus d to the 2s. And you have to be a little bit careful about exactly what c and d you're summing over in this quotient, but you can do that. And when you do that, you realize that for absolute convergence, you need the real part of s to be greater than 1 essentially you're summing, if you imagine that you're just summing over every integer c and d, then it makes sense that you need this exponent to be at least 2. And basically, even after this quotient, you get the same sort of behavior. Now, these Eisenstein series can be made sense of when S has real part less than 1, and we'll see that later. But if you want to use this series definition, then you need the real part of S to be strictly greater than 1. This is kind of analogous to L functions, where if you want to use the Dirichlet series definition of an L function, you need to make sure that you're in the region of absolute convergence.